Chapter 8 is about general concepts in bonding. In this video, we will be looking at sections 1 through 4. In the first section of Chapter 8, we're looking at types of chemical bonds. A chemical bond is a force that holds a group of atoms together to make them function as a unit. So the attraction between the nucleus of one atom and the valence electrons on a different atom. So why do atoms bond? Atoms will bond to lower their potential energy. You can see here in the graph, we've got our atoms bonded together, and you can see that energy is lower than when they are unbonded. So let's get into our types of chemical bonds. First up is ionic bonding. This is when we have a transfer of electrons and cations and anions are created. Opposites attract, and we get an ionic crystal shown here. This typically happens between metals and nonmetals. And you can see here in the diagram, we've got lithium metal and fluorine, which is a nonmetal. Notice the charges, positive and negative. When we have covalent bonding, we have electrons that are shared between typically two nonmetals. When they are shared equally, we call it a nonpolar covalent bond. And when they are shared unequally, we call it a polar covalent bond. An unequal sharing of electrons makes one end of the bond a partial positive and one end of the bond a partial negative. Related to covalent bonding are bond length and bond energy. Bond energy is the energy required to break a covalent bond. This will indicate how strong the bond is, the more energy that's required. The bond length is the distance between two covalently bonded atoms. We will talk about the relationship between these later on in the chapter. When we talk about atoms being bonded to one another, we often talk about the electronegativity of the atoms. This is an atom's ability to attract electrons from other atoms within a chemical bond. As we move from left to right across the periodic table, electronegativity increases. Fluorine has the highest electronegativity out of all of the atoms on the periodic table, so it is the best at attracting electrons from other atoms. Fluorine is a fairly small atom, so its nucleus is close to valence electrons on different atoms, and according to Coulomb's law, that force of attraction would be then stronger. As we move down a group of elements on the periodic table, electronegativity decreases. Atoms are becoming larger as we move down the group. The nucleus of those atoms then would be farther away from valence electrons on other atoms. And according to Coulomb's law, that force of attraction would be weaker. Here is a summary of those trends from the previous slide. The range of electronegativity values goes from 0.7 to 4. We saw that fluorine had the highest electronegativity on the periodic table. When the difference in electronegativity between bonding atoms is very large, we have an ionic bond. When it's very close to 0, we have a nonpolar covalent bond. And right in between, we have polar covalent bonds. So we've been talking about polar covalent and nonpolar covalent bonds. We can also talk about molecules being polar or nonpolar. If molecules are polar, we can say that they have a dipole moment or are dipolar. So basically we end up with two oppositely charged ends to the molecule. One end is more negative and the other end is more positive. You see the water molecule here. You probably remember that water is a polar molecule. So you can see this end of the molecule has a negative charge, and this end has a positive charge. That little symbol means partial, so it's a partial positive and a partial negative charge. Full positive and full negative charges would be like for ions. The three diagrams here for water are just different representations. The one on the right is called an electrostatic potential diagram, where red indicates that there are more electrons. Molecules can also be nonpolar or have no net dipole moment, like with carbon dioxide here. We do not end up with one end of the molecule being more negative and the other end being more positive. These diagrams are three different representations of the carbon dioxide molecule. Pause the video here and try to put these bonds in order from most to least polar. Try not to look up the electronegativity values. Look at the atoms' positions on the periodic table. In A, we're looking at different atoms bonded with fluorine. Carbon is the farthest away from fluorine, so their electronegativity values would be the most different. Therefore, that one is the most polar. Then it's nitrogen and fluorine, and then it's oxygen and fluorine. Oxygen and fluorine are right next to one another on the periodic table. Their electronegativities would be the most similar, and then therefore that would be the least polar bond. In B, silicon and fluorine are the farthest apart, so that would be the most polar. Then it would be carbon and fluorine, and then nitrogen and oxygen, which are right next to each other on the periodic table. For C, boron and chlorine are the farthest apart. Then sulfur and chlorine, they are right next to each other on the periodic table. And then chlorine and chlorine, they are the same atom with an electronegativity difference of 0. Next, pause the video for a moment and see if you can pick out the bond that would be the least polar, yet still be considered polar covalent. The answer here would be nitrogen and oxygen. Magnesium and oxygen, that's a metal-nonmetal combination, so that most likely would be ionic. Oxygen and oxygen are the same atom, so that would be a nonpolar covalent bond. We want to consider the bonds that are polar covalent. Nitrogen and oxygen are right next to one another on the periodic table. Their electronegativities would most likely be the most similar, and then that would make the bond the least polar. And finally, just some final ideas about bonding. When two nonmetals form a covalent bond, they share electrons and they share in such a way that they will have a full outer energy level of electrons. So the valence shell will show a complete electron configuration. And when a metal and a nonmetal form an ionic bond, the nonmetal gains electrons and has the same electron configuration as the next noble gas. The metal loses all of its valence electrons and has an electron configuration of the noble gas beneath it.